Hello, this is Jared Cameron again, and today I'm going to work out a problem for you, a basic kinematics problem that's in one dimension. And so in kinematics, we usually take several assumptions. We assume that the object we're dealing with is a particle, which means it doesn't have any mass or shape. We assume that our acceleration is constant, and we also assume that it's moving in a straight line, okay, which means it's not buzzing all around like a butterfly or something like that. And so when we take those assumptions, we can develop certain equations, and they call these kinematic equations. I'm going to write these equations up here. So these are the kinematic equations. And these equations you'll see in lots of different forms, but they mean the same thing. First equation would be that your final velocity equals your constant acceleration times your time plus your initial velocity. So this sub O here and means initial. The sub C here means constant, so constant acceleration. And then the sub F means final velocity, or the final of whatever that variable is. For our second equation, we're going to have the final position, so S is standing for position. Sometimes people use an X, that's okay too, equals your initial position plus your initial velocity times time plus 1/2 constant acceleration times time squared. Our third kinematics equation is our final velocity squared equals our initial velocity squared plus 2 times constant acceleration times our final position minus our initial position, which is also the displacement if we put it all together. And some people represent that as a delta S or a delta X for displacement. Okay, so the first thing you need to do when attacking a dynamics problem or a kinematics problem like this is to read the problem and try to understand it. So here we see that during a test, a rocket is given an initial velocity upward at 75 meters per second, and when it is 40 meters from the ground, the engine fails. So we're supposed to determine the maximum height and its speed just before it hits the ground. So two things. Let's go ahead and try to look at the first thing. And so after we read it and after we understand kind of what's going on, then it's best to go ahead and draw a diagram to help you organize your information. And so I'm going to draw my diagram where here's my ground. I have my particle here. It's starting at a distance of 40 meters above the ground. Okay, and so my initial position is going to be 40 meters. All right. Now, at each point, I analyze the travel of this particular particle. I want to record as much information as I can. So that means I'm trying to see, hey, do I know the position? Do I know the velocity? Do I know the acceleration? Do I know the time? Okay? And so try to record all of those, or whether you even don't know them, at each point, at each significant point along its path. And so we know our initial position. What about our initial velocity? Yes, we know that too. It says it's 75 meters per second when the engine failed. So 75 meters per second. Okay, what about acceleration? Well, in this case, at the time the meter failed, the rocket rather failed, it is now under free fall, which means that it's under the pull of gravity. Only, excuse me, only the acceleration of gravity is acting on it, and so that's going to be negative 9.8 meters per second squared. And the last thing we record is the time. It's going to be 0, of course, because this is going to be what we consider, excuse me, our starting point. Okay. So it's going to travel all the way up to a point where it stops, and then it's going to go all the way back down to the ground. So these are the other 2 points that I'm going to record data at. And so I'm going to say this is position number 1. Position number 1, I don't know what that is. That's at the height of its travel. That's what I'm trying to find out. Okay, what about the velocity? Well, the velocity is going to be 0 because it stopped and is about to turn back around and go down again. All right, what about acceleration? Acceleration is the same at negative 9.8 meters per second squared because it's still under free fall. And in time, we don't really know what that is. Okay, now when it hits the ground, what do we know? Well, we know that its position, I'm going to call this point 2, is going to be 0 with respect to the ground. Its velocity, we don't know that. Okay, its acceleration, we do know, it's negative 9.8 meters per second squared, always on the free fall. And for time 2, we don't really know that yet either. Okay, and so now we've written as much information as we can from point to point. From that place, what you want to do is understand what you're looking for. In this case, the maximum height, which means that position at point 1, and then you pick two points from which to analyze your kinematic equations. It could be from point initial to point 1, or point 1 to point 2, or point initial to point 2. Okay? But whichever point it is, it has to include the variable that we're trying to find, which in this case is the position at point 1. So I'm going to start with going from initial to point 1. All right? Now, we go through these equations, seeing if we can get a situation with one equation and one unknown. Let's look at this first equation. This first equation is not going to work because it doesn't even have the variable which we're looking to solve. Let's move on to equation number 2. Equation number 2 does have the variable we're looking to solve. It's represented as position final, which in our case is going to be position 1. And so it has that as initial position, initial velocity, but we don't know the time. And so in this case, we're going to end up with one equation and two unknowns. So we don't want that. Let's move on to equation 3. We know the final velocity, which will be velocity 1. We know the initial velocity. We know the acceleration. We're trying to find the final position, which would be position 1, and we know the initial position, which is going to be 40 meters. And so let's go ahead and write out our equation. Fill everything in. So we have v final squared equals VO squared plus 2 times acceleration of gravity times final position minus initial position. So if we look and compare for our final velocity, or velocity 1, which I'm just going to go ahead and change that to so I won't confuse myself. So we're assuming that our final velocity is going to be at point 1. So our velocity at point 1 is 0, so this goes to 0. Our velocity initially is 75 meters per second, so I'll put that there, 75 meters per second, and then that's squared, plus 2 times our acceleration. Our acceleration is always negative 9.8 meters per second squared, times our position at point 1, which we don't know, so we're trying to find, minus our initial position, which is 40 meters here. Okay, now from here, what we want to do is we want to go ahead and solve the equation for the position at 1. Okay, and in doing that, the first thing I'm going to do is I'm going to go ahead and subtract 75 meters per second squared for both sides. So minus 75 meters per second squared minus 75 meters per second squared. What does that do? That cancels out here. Now I have negative 75 meters per second squared. Of course, that is a square term. So I subtracted 75 meters per second squared. What I have left equals 2 times negative 9.8 meters per second squared times this position, or position at point 1, minus 40 meters. Okay. Now, from this point, what I'm going to do is I'm going to divide both sides by 2 times negative 9.8 meters per second squared. 2 times negative 9.8 meters per second squared. Okay. Now, when I do that, I end up having negative 75 meters per second, and that's a velocity. The whole thing is squared over 2 times negative 9.8 meters per second squared. That's going to equal my position at point 1 minus 40 meters. Okay, so to solve for this position, that's going to give me negative 75 meters per second squared. Okay, all divided by 2 times negative 9.8 meters per second squared. Okay, but I have to add 40 on both sides, which will eliminate this 40 here, and get my position by itself. And once you evaluate that, you should get that your position at point 1 is 327 meters. Okay, So I'm going to stop right now, and in my next video we'll go ahead and do the next part of this problem.